Hi, Calculus. It's Mrs. Jarosik. I am coming to you with section 5.4, and we're going to be doing going over the fundamental theorem of calculus today, part 2. All right. So this is section 5.4. There'll be a separate video for part 1. Okay. I'm just going to go ahead and get right into it, only because I want to keep this on the shorter side if I can. Okay. So Roman numeral 1 is a nice little warm up of some of the things we've been doing from sections 5.1 to 5.3. So I actually would like to pause the recording actually and have you do it, as well as if you haven't printed out your own set of notes, you can do that at the same time. But we are going to start with Roman numeral 1, and we're going to evaluate each integral by finding the area under the curve. So that is by using geometry right now. We're going to use geometry to do that. Okay, so I'm going to go ahead and pause this and I will be right back with you. Okay, welcome back. I have my answers written down, and then I have the areas labeled on each of the, I guess, separate parts of the graph, just to go over a couple of things on the picture. So I have an area of a triangle right there and an area of a triangle right there. You may have noticed that they are the same size, if you will. One is under the x-axis, one is over the x-axis. So they would cancel each other out when put together, but individually they have an area of 5/2. Another thing to remember with problem 1, the answer was -6, because remember that areas that fall underneath the x-axis would be negative unless otherwise noted, right, by an absolute value or something else. For the semicircle area, I have my work right here, pi r squared divided by 2. And then for the trapezoid, I have my work down here. Trapezoids always can be made into a rectangle and a triangle if you wish, a right triangle. Okay. All right, let's keep going. So the rest of this page, we are going to explore some ideas with integrals and different function notations, as you can see. So we have 3 different functions going on here. We have capital F, capital G, capital H, right here, capital F, G, H. All right, so all those are different notations for our antiderivatives that are being noted. So they're all representing different area functions. So I guess that is the important piece to take away. But they reference the same graph, which is the graph above. Okay, so all of these are just a very poor bracket, area functions. Okay, so if we start with F, capital F, and we look at the integral that is set up, notice that all of the capital F of X area functions start with a lower bound of -5. Okay, that is our starting point. If we move down to G of X and we look at that, our starting point here is 3 for all capital G of X functions, still referring to the same picture. And then finally H, if we look at H, all of those will start with a lower bound of 7. So what I'd like to do together is go through 5A, 6A, and 7A with you. And again, I would like to pause, have you go and finish the remaining 9, and then come back and see how we did on all of these separate antiderivative problems. Okay, so let's go ahead and do those first 3 all part A's. Okay. All right, so the first thing I want to do is I'm going to set up my integral for myself. So when it says we're going from -5 to x, f of t dt. Okay, well, what we're plugging in for the x value right here is what's in the parentheses, our function notation for that antiderivative. Okay, we're evaluating the antiderivative at -5, which means for the upper bound, we're putting in -5. F of t dt. T, remember, we've talked about this before, would be representative of a dummy variable. Not everything can be the x, because then we would start to not make sense within the notation itself, that we have to have some other variable representing what we're plugging in. Nothing to be alarmed about. It's just you will see that happen over and over and over again to make it a little bit more sensible. Okay, so from -5 to 5, we've talked about this as well. We haven't gone anywhere, right? So we're talking about this is where -5 is. So there's no area to calculate. It's the 0 property for integrals, therefore equal to 0. Okay, let's go to the next one. We're going from 3 to -5, which already seems a little bit strange because that is out of order. And I'm going to actually rewrite that a little bit smaller for myself. Give myself a little bit more space there. So what I'm going to do is apply the order of integration property, and I'm going to rearrange that. And then I will go up to my picture and I will evaluate. So now I'm talking about going from -5 to 3. So that is going from here, -5 to 3. Okay, well, that's the -6 part. And then you've got all of this, which zeroes out, right? So we are talking about -6 plus 0, which is negative, which is, and I'm just about to catch myself. We've got to go back because I had changed the order. So it's the opposite of -6, which is 6. Okay. All right. And then for this next one, we are going from 7 to -5. So we're the same, doing the same that we were doing in the previous part A, where we have to change the order. So opposite sign, switch the order so that the lower bound is the smaller number. And then that gives us the opposite of, so if we go from -5 all the way through to 7, maybe I will give myself a little bit more room by going underneath here. We will get -6 plus 0, and then we have to go all the way through to 7. So that's the 2 pi plus 8 part of the graph, right? So we're going from here all the way through, adding up all those areas. So we've got, within the parentheses, we've actually got 2 pi plus 2. We have to take the opposite of that, so it would give us a final area of -2 pi minus 2, or -2 minus 2 pi. Okay, so now I'm going to pause it, and I'm going to have you finish up the rest of the sheet, and we will come back together in just a minute, okay? So go ahead and pause. Okay, welcome back. Go ahead and start checking some of your answers. And I really want to talk about if there's something that you need to go over, like if you don't agree with one of the answers, go ahead and pause and maybe go back and look at your calculation. But what I really want to concentrate on right now is if you noticed any patterns as you were filling in the remaining answers. So for the sake of time, if you want to pause and then again look at some of this a little bit more closely, what you can see, hopefully, is that when we go from here to here, we're adding 6 each time. When we go from the second row to the third row, we are actually subtracting 2 pi plus 8 each time. Make that fit a little bit. Okay, so definitely see some things happening. So with these antiderivatives, we're using the same function. Okay, so we're using the same function, we're using the same graph. Our starting points for f, g, and h respectively are changing. Their lower bound is changing each time. But with that same function to refer to, we are only differing by a constant. Okay, we're only differing by a constant in all of these situations. Okay, so keep that in the back of your mind. So what I wanted to talk about with regard to this page and finishing up this page is to think about a couple of other ideas. Okay, so if I just take our antiderivative of f from 3 to 7, okay, if I think about that, and I go back to the picture and I can very easily see that that answer, right, we already calculated it, was 2 pi plus 8. Okay, so we think about that, right? It is equivalent to saying, capital F, or antiderivative of f, evaluated at 7 minus antiderivative, capital F, evaluated at 3. So the reason I'm doing this, and it's going to look like I'm almost working backwards for a minute, to just show you some of the notations that we're building, okay? Because some of this notation moving forward is all we're going to see. So I'm just sort of recapping a few things that we've done so that hopefully the notation, it makes more sense, okay? So capital F of 7, what would that actually mean? Capital F of 7, if we go back here to F, right? If I put in 7 right here, it's going to be exactly what we wrote here, okay? So if I did capital F of 7, remember what that means. We start at -5, and we're going to go to 7, and we're going to subtract. Same capital F function, so starting at -5, but this time going to 3, right? And then keep building. So if I go back and I look, that was equivalent, that from -5 to 7 piece was 2 plus 2 pi minus, and then from -5 to 3, I have that one up there as well, is -6, which gives us 2 pi plus 8. Okay. Remember when I was saying before about how this is all the same function, we have different antiderivatives that just start at different lower bounds. Okay, so please keep that in the back of your mind right now. So let's go with, how about if I say it's equal to capital G of 7 minus capital G of 3. So my antiderivative of the function f of t dt taken from G always started at 3. So from 3 to 7. And from 3 to 3. Recognize that one. So what we're saying again is that I just have to reference back. So 3 to 7 on G is right here. And that was equivalent to 2 pi plus 8 itself, right? So 2 pi plus 8 minus, and then from 3 to 3, right? That's that zero property of integrals. So we've got 2 pi plus 8 as our answer. We're seeing some patterns. And then finally, we've got H. So capital H of 7 minus capital H of 3. It's going to be no surprise. We're going to end up with 2 pi plus 8. Bear with me. So H of 7 was from 7 to 7, f of t dt. So that's our 0, if you will, minus. And then when we do H of 3, we go from 7 to 3 f of t dt. So remember that that is order of operation is it's out of order, if you will. So I need to also take the opposite of whatever that is. And then that was 2 pi plus 8. Okay. So the opposite of that, but then you're subtracting, so you end up with positive 2 pi plus 8. Okay. So let's go back to red. Okay, so we have all are the same function. So all antiderivatives are referencing the same function. So the starting point doesn't matter. Okay. All right. So let us go to the next page. We're building some patterns here. So what we had said from row 1 to row 2 was, and row 2 to 3 was that they only differed by a constant, right? So keep that thought. Remember I said to keep that one also in the back of your mind. So on this next page, what I would like to do is go through the first part of the exercise together, pause, have you do the second part on your own just to get some practice, and then come back together and make some final conclusions before we do some practice problems using fundamental theorem part 2. Okay. All right, here we go. So we have a completely different function now, and we actually have the function. So 2x minus 4 is our function. We're going to determine 2 different area functions using geometry again. Okay. So after this lesson, a lot of the geometry, unless you're specifically asked a Riemann sum question or a trapezoidal sum question, or in the rare case of something that can't be calculated without geometry, we're not going to do very much more geometry from here on out. Okay. Everything now is being built up until now with geometry, so you can see what we are calculating. So you can see and understand all of these different shortcuts and tricks that we come up with, where they're built from. Okay. So consider this maybe one of the last times we're going to be using geometry so much. All right. So we're going to determine the 2 different area functions. Let's start with capital A of x. That's our first area function. Okay. An antiderivative. That capital A is your signal, right? Those capital A of x, capital B of x signal that that's the antiderivative's name, the function name. Goes from 3 to x. All right, so I'm going to put some labels on the picture. There's 3. X is arbitrary, right? We don't care. So let's say that's x. Okay. And what we are going to do right now is using whatever shape I just created, which it happens to be, hopefully you see that, it's a trapezoid. Not such a great line. Let me try that one more time. There we go. Okay, so we're going to use the area of a trapezoid. And that is 1/2 base 1 plus base 2. So base 1 in this case, well, if I plug 3 in, I get, right, 2 times 3 minus 4 gives me 2. So my first base is 2. Now, if I plug x in, that should make sense, right? We get the f of x itself, which is 2x minus 4. So until I know what x actually is, it's 2x minus 4. And then my height of the trapezoid is right here. So that means it's x minus 3. Okay, so just have some algebra to do now. So I'll distribute that half through there. Okay, and that is my area when my starting value or my lower bound is a 3 on my function 2x minus 4. Okay, now what we're going to do with the next b of x, the next antiderivative, we're going to go ahead and do the same thing, except we're going to start with a different lower bound. So let's start with 5. Let's go ahead and start with 5. And calculate, I'm going to pause. I'll have my work down, and then you can go ahead and do what we just did and calculate the area using the trapezoid that's drawn. And speaking of drawn, let's go ahead and at least get the picture. Let's make that x. This is 5. Go ahead and calculate the new area or the b of x function. Okay. Okay, welcome back. Go ahead and check your work against mine and see if you agree. And there's something that's happening here that was happening in the last set of problems as well. And hopefully you have noticed that they only differ by a constant, right? Our area functions only differ by a constant, right? Okay, so let's make a generalization real quick. We can say capital F of x is equal to x squared minus 4x plus c. Now that should ring a bell from 5.1 when we just talked about antiderivatives in general, right? And we needed the arbitrary constant. So any area function is an antiderivative of f. Right? So capital F of x, any area any area function is an antiderivative of f. All right, so I'm going to generalize even some more at this point. And finally, we're going to come to the conclusion of what is actually the fundamental theorem part 2. Okay, so we've seen this differing by a constant the whole way through. So let's just take our f of x. I'm just going to write it down here as well, just so it's closer to where I'm writing. We're taking our generalized, right? Okay. So if I say our lower bound is a, our upper bound is b on f of x dx, okay? And we are going to say, and this is from what I worked out on the previous, excuse me, I'm just scrolling up to remind you. So when I spelled out with actual values in it, something to this effect, and showed how all of this takes you back to that same answer. Okay, I'm going to do the same thing right here. I'm going to say that once I've taken my antiderivative, I have to plug in my upper bound and I have to subtract my lower bound plugged in. Okay. And if I were to bring it even back to what we just did with, let's just go a of x, capital A of x. Okay. And I make it more specific to show we went from 3 to x on f of x dx. That would be equivalent to capital F of x minus capital F of 3. Okay. And what would this mean? What would that mean? I am taking the x and I'm actually plugging it into the antiderivative, which is just the antiderivative itself, which is right in front of me up here. So it would be better to have the writing tool, x squared minus 4x plus c minus, now I'm going to take the antiderivative and I'll plug 3 in there and there. So I have 3 squared minus 4 times 3 plus c. Okay, so x squared minus 4x plus c minus 9 plus 12 minus c. Oh, look at that. X squared minus 4x plus 3, which is what we had gotten with a of x right here. Okay. All right. What I want to do is give you officially the fundamental theorem of calculus. Believe it or not, I've already written it down. I just didn't bring your attention to it quite yet. This is the fundamental theorem of calculus, part 2. It's the evaluation part. That's a lot of times what it's called. Because you have a definite integral, okay, definite integral, you'll have a lower bound, you'll have an upper bound. You'll have an A, you'll have a B. You will calculate your antiderivative, not by geometry necessarily, and probably most of the time, not by geometry. And you will plug in your upper bound into the antiderivative, and then you will subtract the lower bound plugged in to the antiderivative, okay? The only notation piece I did not put on this paper is this. You've seen, I know my students have seen me do this before, and I am venturing a guess that both Ms. Gogarty and Mr. Leavenworth have used this notation before as well. But by putting the evaluation bar down, right, that is equivalent. This statement is equivalent to this statement is equivalent to this statement, okay? And if we just carried this down here, it would mean that we're doing this. It's the same idea, okay? You will be using that notation frequently on these, and whether it's, sometimes I used it with derivatives, right? Some of you recognize that, and we will continue to use that all of second semester as well, okay? All right. We're gonna do some practice problems, okay? So we're gonna do 2 indefinite integral problems, and we're gonna do 2 definite integral problems. So these are indefinite. As a refresher, we're talking about this, are integrals with no bounds, right? So you need plus c, your constant of integration. And a definite integral has bounds. Maybe instead of just generalizing so much, lower and upper bound. Right. And this is where you're going to be using your fundamental theorem, part 2. Right? So just for good measure, since you just learned it officially, right? Finishing off my new evaluation, capital F of T from A to B, right? All right, so let's go ahead and look at these. So you have a series of antiderivatives that you're going to want to memorize, but when you think of your trig derivatives, I said derivatives, when you think about trig derivatives, if you think like d dx, right, sine x is cosine x. So it works in reverse, that the antiderivative of cosine is sine. And if we think d dx of cosine x is negative sine x, the antiderivative of sine has to be the opposite of cosine, okay? And I made a slight error on my antiderivative notation there that I probably, right, they should have their dx's on them. Okay. All right, so the integral or antiderivative of sine x would be negative cosine x, right? Plus c, we need the constant of integration. And that's all that problem requires. Now with 1 over x, this is one of our special antiderivatives. We don't, obviously, if you think x to the negative 1, if you think x to the negative 1, like a rewrite, you can't add 1, you get 0, and then you'd have to divide by 0. So you can't actually use a power rule here. So your antiderivative of 1 over x is ln x plus c. Now, to make it even more special, let's look at our graph of 1 over x, right? So 1 over x looks like this. Notice we have the only x value, your domain, on 1 over x, right? Your domain is all reals. X cannot be 0. But notice we do have negative x values, right? With ln x, we know we can't take the log, natural log, common log, any kind of log of a negative number, therefore requiring us to have an absolute value on that. And if you actually think about the graph of what the absolute value of natural log would look like, right? It's still, that was horrible because it wasn't symmetric at all. Sorry about that, everybody. I could do a lot better than that, and I could do better than that, but I think you get the idea. It's kind of making me crazy though. All right, let's try that again. I'm going to try and make this as, I think the harder I try, the worse it gets. Okay, there we go. So your natural log absolute value of x graph would look like this, where we can have our negative values represented. What's the important part about this? It's that when you're answering any type of question having to do with the integral of 1 over x, when you first on a free response write something out, you want to make sure that you do have your absolute value sign on it, because otherwise it would technically be incorrect. It's a minor error, but it's an error. Okay. All right, so let's go to our definite integrals. This is where we're going to actually use our fundamental theorem. So that means I'm going to calculate my antiderivative. Yay. Okay, so now we're going to use calculus, power rule. We add 1 to the exponent. We divide by 3, which would give us a 1 as a coefficient. And here we add 1 to the exponent, which would make it a squared. And when we divide 4 by 2, we get 2. We don't need plus c. We are evaluating. There's my evaluation bar from -1 to 2. So when we go ahead and plug all this in, it should be 2 cubed plus 2 times 2 squared minus -1 cubed plus 2 times -1 squared. 8 plus 8. And then this is -1. That's positive. Ooh, well, where did that go? That is +1 when I square, right? Times 2. So that's plus 2. 16 minus 1 is 15. So what I'm going to do right now, actually, is I'm going to, let's see if I can do this. I'm going to pause and bring up my dot camera with the calculator, because I do want to show you a couple of keystrokes in the calculator on the TI, so that you are familiar with how to use your integration menu on the calculator. Okay, so bear with me. Okay, everybody, we're back with the calculator. So I just quickly rewrote, so I don't have to go back to the other screen before we finish the video. I quickly rewrote out the 2 problems I want to show you on the calculator. If you hadn't been shown this prior to this video in class, on the TI, you need to hit your, so I can show you the keystrokes themselves. To get to the menu where the integration is the same place the derivative menu was. So you're going to hit the math button, and it is choice 9, FNINT. All right, let's go ahead and do the one we just did and check our answer. So you're going to have a space for your lower bound. You're going to have a space for the upper bound. You're going to type in your function. Remember, I showed a little bit of this to my class beginning of the semester, that if you use the Y1 menu and plug things in, you can always just go retrieve Y1. So any function you put into your Y menu, the graphing menu, you can go retrieve, and then you wouldn't have to retype the function over again. All right, 15, we did a good job on that one. All right, and if I do math and 9, I'm going to go ahead and calculate from e to 3 ln x dx. The reason I am doing this one by calculator only, it is only a calculator problem. We do not manually calculate antiderivatives of natural log. We don't learn that one, okay? That would only appear on a calculator portion of your exam, any exam within class or on the AP. So second, to get to the E button, second and the division key. Upper bound 3. ln is found underneath log, L-O-G, so there's ln right here. Natural log x. Close my parentheses, and I need the dx with respect to x. All right, so remember 3 decimal places are necessary, so I should have an approximation sign, 0.295 or 0.296. Either would be correct. Okay, I'm going to close it out here. It's been long enough. Thank you for your attention. And remember, you can always listen to any videos you want on a faster speed. I should have said that at the very beginning. I should have said that. But have a good day, and we'll see you in the next video, okay?